arbitrarily, we just chose a range of about 5 to 18. And this is for 75% power. And this is a plot of all of the points of our mean outputs versus our inputs. And this is also presented with error bars for 95% confidence interval. And so our best fit line here gives us a pressure equals 0.58 of the input percent for slope. And for our step function, the whole point of the step function was determined what they call the first order plus dead time parameters. The step function itself consists of you start at one input and then give it a step size. Personally, I use 35%, just chosen arbitrarily, either up or down, so that you could calculate these parameters based on the change of the system between the two steady states. And so the three parameters are the dead time, which is sort of the time that the system takes to respond to an input, the time constant, which is the amount of time it would take for the system to get 63.2% to the next output, and then the gain, which is, again, it's in units of input or output over the input. And then the gain should correspond to the slope from the steady state operating curve. And the whole purpose of finding these constants is that they are used in transforming a function from the time domain to the Laplace domain. So this is an example of one of our step up responses, and the green bar here represents actually the plotting of the steady state means that I used in some of the calculations, and my red line here is at the step size at 15 seconds, and this is an estimate of the sharpest slope for this curve. And so the dead time estimated from here to here is about 0.1 seconds for this, and our tau would be about 63.2% up the slope of the red line. And then our gain is simply the difference in the means over the step size, which in this case was 35%. And this is an example just of one of our down steps. And the only thing I really want to point out with this one is how much less steep the line ends up being. It takes more time for it to reach its stepping down, it takes more time to reach its steady state. What that ends up corresponding to is a larger value of your time constant. This is our determinations of our dead time. And you can see just think of all of our experiments, I had one that was different. All the others was close to just 0.1 second when you looked at down to just tenths of a second. So we had no uncertainty for these, and then say about 0.2 for this one. And as I mentioned before, we can see the differences in our time constants. The down steps are all significantly longer than our up steps. It will take longer to reach that next steady state. And, so our gains were within 0.8 to 0.5, which averages to about 0.6 centimeters of water per percent. This red line represents the slope from our steady state operating curve to compare our values of dead time. And these were gain, and these were really consistent in that only even one of these had uncertainties within the tenth of a second, tenth of a percent. And so, in conclusion, our steady state output was about 0.58 centimeters of water per percent. Our dead time averaged to 0.1 seconds. Our time constant came out as 0.6 seconds, which matches up very nicely with the slope from our steady state operating curve, and our gain comes to 0.6 centimeters of water. Mix of 0.6. And
Hey. There you go. Merry Christmas. What color was he? He's John Gutford. What was the red?
If you were a presenter, remember to pick out one or two of those feedback forms, one of your peers, and give it to me and say, hey, this one benefited me with this feedback. Hey, what do you see here?
A lot of stuff.
A lot of stuff.
Some lines.
How about a graph made by Excel with a number of data points on it? Guess what? Those data points are not exact. They are just data points. So look at this. This line happens to be 3 of those in a straight line, but look at all these other things. So can we take, if you put your mouse over that value, you know, it'll tell you what value it is. Am I right, David?
Yes.
And what is, when you put your mouse over it, does it give you more than one significant figure? Yes. Usually 6 or 7 or 8. It's worthless. because look at this, look how erratic that data is. So use approximations when you're doing this thing. Anything else I need to say? All right, let's go and talk about something else. Questions? Say it again.
The arrows, don't they make it harder to read, to grab?
What, the green, the red, and the blue? The arrows make it harder to read the graph?
It makes it easier.
Makes it busier? All right, we're gonna vote on this. These arrows here you're talking about. So, if that arrow wasn't there, there's something here that, what color is that? Does everybody know that's blue? No, if you're colorblind, you don't know it's blue.
No, they've used different shapes.
Different what?
Shapes.
Shapes, oh, so you're gonna give different shapes. Oh, okay, so these are squares, and these are,
Squares.
diamonds, and these are triangles. Oh, that's pretty demanding of observers. Your job is to make it not demanding for the people who are looking at it. So let's vote. You like the arrows that go from the name of the curve down to the curve? Like these? Or you think you raising your hand?
Yes.
Is that a yes? Well, hold on, I'm gonna make sure everybody understands the question. Or you want no arrows in order to clarify, what's the word?
Make it less busy.
Make it less clutter, to reduce clutter. Well, reducing clutter is a good thing, right? And making it clear is a good thing, right? So we're gonna vote. How many want the lines like this to help the observer know which is which? Raise your hand. 1, 2, 3, 4, 5, 6. That carries. Okay. Pardon? Okay, okay. Did that answer your question, David?
Yes.
What's the answer?
We're not using lines.
We didn't vote. Nobody voted for not using lines.
Well, there was two options, people voted for using.
There was only one option, you only voted one way.
This is Russia, don't you know? You vote, that's it. Huh? End of story. I don't know if it was Russia or not. Excuse me if anybody's from Russia or feels obliged.
I think we're still the only thing on one picture. Good job.
Joel, you notice
Still
that
the only
Aaron's
two on one
name's not on
picture.
here anymore?
What?
Aaron's name's not here anymore.
Is he no longer with us?
Pardon?
Is he no longer?
Well, he's not on Blackboard list, so I guess he dropped it.
Yeah, I'll send you the,
Let him have to take an exit picture.
Aaron dropped.
Pardon?
He did.
We can just vote.
He dropped it. All right, weekly assignment schedule. This is, looks like we're in week 5. We're gonna model, with the first order plus dead time model for your lab system. This thing here was just for fun. Somebody showed us that. Who was it? You, Ryan? Your last slide showed us the result of your model? That was just for fun, just to get you warmed up in Excel formulas and drawing curves. This time, all right, let's do this. Should we do this the easy way or the hard way?
Easy.
Okay, here, the model you had last week is going to be modified. Tells you how to do it. How to do it. Tells you how to do it. You want me to read all these to her, or you're going to read it yourself?
We know how to read.
Yeah, you just add on, add on, add on, add on. There's a, okay. I've been able to read it. Now, if you follow all those instructions, you'll get a new Excel file, or if you click on here, you'll get the file. So would you like to click on here?
Let's click on here.
Is there anybody knows how to tell Windows that when I ask it to do something, I want it to do something rather than ask me if I want it to do something?
That's not what it does, it's Internet Explorer, it's probably in the settings.
Thank you. Find out how. Overcome. All right, here's the spreadsheet. Let me show you. That differently for a minute here. That's a little bit. That's a lot of stuff. Notice the first three columns are the same three columns that you had before. What are they labeled?
Time, input,
Time
output.
input, output.
Time, input, and output.